guys, in this video I'm going to just go over 6.1. This first shot here is just of the vocab for this unit, so if you want to pause the video or take a second to look in your book and get these definitions, that's a good idea to get started. So one of the things we're going to be talking about in this unit is polygons, and so we want to define some different ones. This table is going to be helpful for identifying what we call different polygons depending on how many sides they have. Poly means many, and so what we consider many is 3 or more. So the smallest polygon we can possibly have is a triangle. And we can have infinitely many number of sides, so once we get past 12 we just call it an n-gon, where n is the number of sides. So for example, if it has 15 sides, we just call it a 15-gon. These are kind of some more common ones from anywhere from 3 to 12. The word regular in front of polygon just lets us know that all the sides and angles are congruent. Concave, that's if I want to connect, a diagonal is a line connecting two vertices together that aren't right next to each other. So if I connect these and notice it's outside the shape, that's what we would call concave. If I do that in this figure, it's convex. Those diagonals never are outside of the polygon. Just like we know a triangle has 180 degrees total inside, we can figure out how many degrees total make up any size polygon, and this is our formula for it. So n is just the number of sides, so if it's an octagon we put an 8 in here, and we do that number minus 2 and then times 180, and that'll tell us the total number of degrees within any given polygon. We can also look at the sum of exterior angles, so that's if we like extend each of the sides outward. One angle at each vertex, they will always add to 360 degrees. Okay, so we're going to use those definitions and properties to do a couple examples here. Okay, so in 6.1, we're going to have to tell whether or not each figure is a polygon. So remember, it has to have at least 3 sides, and it has to be complete, like one vertex to the next, connecting without crossing through itself. So this one is, it's a polygon, and we want to classify it by the number of sides. So this is where looking at this table on the previous page will be helpful. So in this one, I think I have 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. So this is a 9-sided figure, meaning it's a nonagon. So I'm going to say yes, it's a polygon, and call it a nonagon. Okay, this one is also a polygon. Every vertex connects to itself. There's no like crisscrossing or overlapping. And this one I believe has 8 sides. Yep, and so it's an octagon. Now this one might look kind of funny. You're like, wait a second, I know what an octagon looks like. The one we typically see for like stop signs is what we call a regular octagon. This one is not a polygon because it's crossing through itself, because I can't determine is this part a side or is this whole thing a side. So if there's any discrepancy on that, or again that crisscrossing through itself, this is not a polygon. It's 2 polygons connected to each other, 2 triangles, but together it is not one. So we just say no, and if it's not, we actually can't name what kind it is. Okay, next we're going to decide, is it regular or irregular? So regular, remember, means all the sides are congruent and all the angles are congruent. Irregular is any other option. Convex is if I connect the diagonals and they stay inside the polygon. And concave is if I connect a diagonal and it ends up outside the polygon. So in this one, this is regular. From all those markings, I can see all the sides are the same and all the angles are the same. So this is a regular polygon. And it is convex. So if I connect any diagonal, they're all going to remain inside the shape. So we would say it is convex. What helps me remember the difference? Concave is like it's caved in at a certain point. That helps me remember which word goes with which style of polygon. So in this one, I don't have all the sides the same length. These ones have the double tick mark. These ones only have 1. So this is an irregular polygon. And see how it's caved in right here? So if I were to connect this diagonal to this diagonal, it'd be outside the polygon. So this is a concave polygon. Okay, so now we're going to use the interior angle formula, the n minus 2 times 180. So what we're going to do to find the sum of all the angles in a convex 15-gon. So 15-gon means there's 15 sides, so I'm just going to plug in 15 for n. Okay, so I'm going to do what's in these parentheses first. So 15 minus 2 is 13, and then 13 times 180. So if I do 13 times 180, I get 2,340, and that's total degrees. So just like a triangle has 180 total degrees, this convex 15-gon has 2,340 degrees total. Okay, this one is similar, but it's actually asking for each specific angle of a regular decagon. So regular means all the angles are going to be the same. And then deca, if I look back at that table, deca means 10. So there's 10 angles and they all happen to be exactly the same. And I know that all 10 angles have to add up to a certain amount, and to figure out what that amount is, I'm going to use that formula one more time. So I'm going to plug in 10 for n. So I do 8 times 180 then, and if I do 8 times 180, on this one I get 1,440 degrees. But they want to know each angle. So this is total, all 10 angles together, but if we just divide by 10, since they're all the same, that'll give me 144 degrees per each angle. Okay, this last example is dealing with the exterior angles, where I know all of the exterior angles have to add up to 360. So I'm going to set up an equation to find r. So I'm going to set up 4r plus 8r plus 5r plus 7r. So I'm adding all 4 of those exterior angles and setting it equal to 360. If I combine those like terms, I get 24r total, and then just divide both sides by 24 to get r to equal 15. All right, that's all the examples for 6.1. Thanks for watching.